Hi there. This is the first video of a two-video series on the question of face alignment. And the targeted audience of this video is college students or graduates that are majoring in computer science or engineering or science major. Now the question of face alignment is given a picture with a human face there. It tries to align a shape to the human face. And specifically, the shape is composed of a few landmarks. In this case, in this picture is 192. And these landmarks compose the shape. And once it's aligned, we will know where the eye of the person is, where the mouth is, where the nose is, and the boundary of the face. We can extract these informations. Now let's first have a look at a demo of this method. Here is a video of a person, and for each frame of this video, this method is applied. So it's like we're tracking the face of this person, but it's not. It's actually applied to each frame of the video. And here we get an application of this method. For example, once we are able to track the eyes, we can put interesting things on the eye, or for the whole face, we can put a mask here. And this app and this team has been bought by Facebook by $2 billion US. So this technology really can make money. Now the common way to do it is using machine learning. So for machine learning, it has two stages. One is training and another is testing. For the training stage, you will use a lot of pre-labeled images. So we have a human face and we label where the landmarks or the shape should be. And we have, say, thousands of images, and we use this input data to train a prediction model. And once the prediction model is trained, then we go to the testing stage, and that is, or you can say prediction stage, that is given an input image. Using the prediction model, we'll be able to find the shape or the landmarks. So there are two questions involved. One is, how is the model applied to find the face pose, to find the shape? And another is, how is the model trained from thousands of images? So in this first video, we're going to answer the first question, meaning we're going to go through the testing stage and try to understand the mechanism. Along the way, we will be able to understand what is inside this prediction model, what are the parameters that are essential to the prediction model. And once we understand that, we'll talk about the training stage in the next video, and we will tell you how the parameters in the prediction model are found. Now this video is mainly based on these two papers. The first one, this one is done by Microsoft Research Asia, and it has received more than 480 citations. And this paper is a more recent paper, and we're mostly going to talk about the mechanism described in the first paper. But these two are actually very similar, and because the second paper has better images, so we use most of the images from the second paper. Now let's dive into it. So first we're given an image in the testing stage, and we are trying to find the shape, the landmarks on this image. The first step is to do face detection. And after face detection, we get a rectangle of the human face, like this. Now there are many different face detection methods, and it's not the focus of this video. Once we get the face detection, the next step is we're going to take the mean shape. We call the mean shape shape 0. We're going to take the mean shape from the prediction model and we're going to apply it to the rectangle that we get from the previous stage. Now, by the way, when we go through this testing stage, I want you to keep this question in mind, and that is, what are the parameters in the prediction model? So for example, we just talked about one type of parameter, that is the mean shape. Okay, now we have the mean shape, we call it shape 0. And then we extract 400 pixels from the image based on the location of the shape. And then we apply the first stage regressors. And after the first stage regressors are applied, we get shape 1. Now, comparing with shape 0, we can see that shape 1 better approximates the shape of this human face. And then, from shape 1, we will extract another 400 pixels, and we are going to apply the stage 2 regressors, which are a different set of regressors from the previous stage. And then we get shape 2. Now, shape 2 looks even closer to what the human face should be. And then for the next stage, again, this process is repeated. Another 400 different pixels are extracted, and the stage 3 regressors are applied, and then stage 4, stage 5, and so on. And until stage 10, we will get the shape like this. Now this is much more ideal and closer to the desired result. So this is the overview of the testing stage. We do a face detection, and then we map the mean shape, and then we regress it using the stage 1 regressor, and then stage 2, stage 3, and so on, until stage 10, we get a much better shape. And all the different stages, the mechanism are basically the same. So as we dive into how exactly one stage is performed, we will take stage 2 as an example. Now first, the 400 pixels are extracted, and then the regressors are applied using the information from the pixels. So how are the 400 pixels extracted? Here is the image, and the 400 pixels of a certain stage, the location of the pixels, they are stored in the prediction model. And we will always use the mean shape. We apply it on the image according to the face detection rectangle's position. And relative to this mean shape, indicated by the yellow dots, we will put the 400 pixels here. And then the 400 pixels would go through a similarity transform. And then the pixels would look like something like this. So the location is going to be changed. And this similarity transform TS is obtained by comparing shape 0 and shape 1. So TS is the similarity transform that roughly changes shape 0, these yellow points here, to shape 1, the yellow points here. And once we get this similarity transform, we can apply it to each of these red dots, which are the 400 extracted pixel points, the locations. Take an example for this pixel. Let's zoom into it. For this pixel, we will find its closest landmark, which is this one. And we will find its coordinate with respect to its closest landmark. We get x and y. And then we apply the similarity transform to this pixel. Now the similarity transform TS is applied to x and y, multiplied into it. And with respect to the same landmark in shape 1, now we find the location of this pixel. So we would apply this to all the pixels here, and we get the 400 pixels and their locations. So based on these locations, we can extract their intensity value, and these are the samples from the image that we're going to use to apply the regressors. Actually, these are the only information from the image that is going to be used as we apply the stage 2 regressors. Now, what is the regressor? All this information of the regressor is also stored in the prediction model. So for a regressor, it has a lot of ferns. It's composed of, say, 500 ferns. Fern 1, fern 2, all the way to fern 500. All these ferns, the structure are identical, but the parameters inside are different. Now, as we go into it, you might have questions like how these pixel indices and these thresholds in the fern are determined. So these are very valid questions. It's a very good question, but it's not going to be the focus of this video. We're going to talk about how the parameters are found in the next video in the training stage. Now, in the testing stage, let's just assume that these parameters are already found and stored in the prediction model. So now, what is the fern? A fern can be thought of as a constrained tree where the same binary test is performed at each level of the tree. It helps to split data into different groups. So here on the left-hand side, we have a classification tree. And at each node, a different question is asked. But for a fern, at the same level, we ask the same question. For example, in level 1, the same question is asked. So a fern can also be represented in this way. And this is a fern. On this fern, on every stage, we will ask a question. And the question is this. We will pick 2 pixels from the 400 pixels that we have just extracted. These 2 are just the indices of the 2 pixels. Let's say we pick these 2 pixels. We're going to compare the difference of their intensity with the threshold. And if it's greater than the threshold, we go one way. If it's smaller, we go the other way. Now let's say it is greater. So we pick the way on the left. And then on the second level, we ask a different question. And similarly, we pick another 2 pixels. Let's say these 2. And we compare their difference with the threshold. And then we go to, let's say it's smaller than the threshold, so we go to this split. And then the third level, a different question is asked. On the fourth level, another question is asked. So it goes down until it reaches a leaf. And on the leaf, it stores the information of a delta landmark. For all these 16 leaves, a different landmark is stored. And as we go to this leaf, we add the landmark of this leaf to the current shape, which is shape 1. Now here is a typical value of this delta landmark. In this video, we have 194 yellow points. And this delta landmark is a 388 dimension vector where it stores the x coordinate and y coordinate of the first landmark and the x coordinate of the second landmark, y coordinate of the second landmark, and so on. So all the small delta value for each of these landmarks, x and y coordinates, are stored in this delta landmark. you can see that the value is very small. This is a typical value that is extracted from a real model, a real prediction model. You can see the value is very, very small. So a very small modification is applied to this shape, changing it a little bit. Now we have applied Fern 1. And for Fern 2, similarly, at each level we ask a different question, which is also different from Fern 1. We use different pixels selected from the 400 pixels. And we go down, we traverse this fern, and we find a different delta landmark. And we also add this delta to the current shape. And it goes on and on until we go to the 500th fern. We traverse this fern and we add another landmark. So as we apply the whole stage 2 regressors, we would have added 500 different delta landmarks to shape 1. And that would change shape 1 from looking like this to this, better approaching the desired result. So this is how it works on a stage. Again, first we extract 400 pixels. We would apply the similarity transform according to shape 1, so that the pixels would be more closer to the face. And then using these 400 pixels, we would traverse all these ferns to reach their leaves. And at each leaf, we get a different delta landmark. We add them to the shape, and in the end, we get shape 2. Now we understand the stage 2 regressor. The stage 3, stage 4, they're basically the same. And it goes on until the 10th regressor, and we get this result. So again, this is the flow. And to answer the previous question we asked, what are the parameters that are stored in the prediction model? Here is the answer. First is the mean shape, shape 0. And then there are 10 stages of regressors. For each stage, there will be the locations of 400 pixels stored in the prediction model. And also there will be 500 ferns. And at each fern, there will be 1, 2, 3, 4 questions. And each question has the index of the pixels to be selected from the 400 pixels and the threshold value. And also each fern has 16 leaves, where each leaf stores a delta landmark. Now pay attention, these numbers, like 400 pixels, and the number of ferns, and the number of stages we have in the tree, which results in the number of leaves we have in the fern, the number of stages in the fern. All these numbers, they can be set by someone using this model. When you train the model, you can choose that, okay, I don't want 400 points, pixels. Let's say we have 300. Or maybe we want 500. It's all up to you to choose these numbers. Or let's say we want 400 ferns. And for each fern, we only need 3 stages. So if there are only 3 stages, then there will only be 8 leaves here. All these can be set by the user in the training stage. But these values is 400, 500. All these values, they are the typical values that are used. And by the way, the number of landmarks can also be set. So here we have 194 landmarks, but you don't have to use 194. In fact, very often people use 68 landmarks. For example, in MSQRD, they use 68 landmarks, and that's usually good enough. Now, by the way, the author calls this method a two-level boosted method, which means before this paper was presented, most of the existing methods, they only use a one-level method. So they do not have stage 1, stage 2 until stage 10, but they will have a very big stage 1. So just one stage. They're going to extract the pixels, and then they're going to apply, let's say forward in one stage we have 500 ferns. So here it's only one stage, so it's going to be maybe 5,000 ferns. They're going to apply 5,000 ferns, and they will take the result as the final result. But the author of this paper, they divide it into 10 stages. And for each stage, they will extract a different set of 400 pixels. And these 400 pixels would be changed according to the current shape. Now this is different because before in the only one level type of method, the pixels will only be mapped according to the mean shape and only once. But now it's going to be mapped according to the shape of the current stage. So this way, these 400 pixels will be much more relevant than the only one level method. And this is why this method is more accurate and achieves better results. Okay, so this is the testing stage. And now you must be interested in how the location of the landmark of the pixels are decided, and how the information like the index of the pixels and the threshold are set. And that question needs to be answered in the training stage, which shall be the next video. And here is the pseudocode of the testing stage. You can pause your video to have a look at it. So thank you for spending your time to watch this video. Give it a thumb up if you like it. See you in the next video. Thank you.